So in that column, sorry, in that chart or in that table, we had rows for shunt chopper, series chopper, their on and off errors. And that was for the case whereby RG, the generator resistance, was equal to 0 for various values of load resistances. So the load resistances typically are the input to the AC amplifier. And that table, we computed the on and off errors for series and shunt choppers for various values of load and generator resistance equal to 0 to check their performances. What is the on error? What is the off error for the series and shunt, so that we can make a decision as to which switching configuration we should use. And we found that in general, the series chopper was outperforming the shunt chopper in terms of the errors. Now we have another switching configuration, which is called the series shunt chopper. So in the series shunt chopper, this is how the transistors are connected. So this is the figure. You got your generator, you got your generator resistance, RG, you got your first FET over here, which is in series with the load. And then we got your second FET at the bottom over here, which is in shunt with the load. So this configuration is referred to as a series shunt chopper. So once again, we are going to analyze the switching errors, the on error, the off error, and then we'll put it in the same table. I give you as assignment to put it in the original table, because the original table had only series and shunt. Now you can put it in the same table, use the same level of signal, in general VG, and then find out the on error, the off error, and therefore we can make a decision as to which switching configuration or which switch configuration we should use to give us the least error. So we'll just go quickly through this configuration, which is referred to as the series shunt chopper. So as I said, it's called series shunt because we got two transistors, one in series and one in shunt. Okay, so we'll just go to the error. So to analyze the error due to the series shunt, when the series device is on and the shunt device is off. So this will be equivalent to like the on error, because that is when the switch in series is supposed to send all the signal from the input to the output. But because the switching devices are not ideal, they generate some error. And in this case, we'll refer to this case 1 as our on error. So our on error for the complete configuration is given by indicated minus true value. So if the series device is on, ideally, the indicated should be the total voltage generated by our generator. So our indicated will be our voltage appearing across RL, which I'm calling VL, and our true value is supposed to be VG. So the error is indicated minus true, which is VL minus VG. So VL, if I combine these two resistances, RDS off and RL, and call it one name called R equivalent. So VL will be VG into R equivalent over RG plus RDS on plus R equivalent. Okay, because I've combined these two at the output as one impedance, I'm calling it R equivalent. So this effectively forms a series circuit from RG, RDS on, and R equivalent. So you get equation 2 over there. So we'll just simplify equation 2. So first I'll get VG common in equation 2. So I'll take it outside the mini bracket. So if I take it outside, actually I've taken minus VG as common. So if I take minus VG outside, then I'll get it as 1 minus R equivalent all over RG plus RDS on plus R equivalent. Because if you expand this equation, let's call it equation 2b. Let's call it equation 2b. If you expand equation 2b, multiply Vg inside, you'll get minus Vg plus Vg into R equivalent, all divided by Rg plus RDS on plus R equivalent, which is the same as equation 2. Okay, but we want it in the form of equation 2b. So if you make a common denominator, which is Rg plus RDS on plus R equivalent, then the numerator, I think I've done this in the last class. So the numerator, there's supposed to be equation here. So let minus Vg all into Rg, RDS on, plus R equivalent, and here you'll get Rg plus RDS on plus R equivalent minus R equivalent. So this could have been equation 2c. Okay. So this R equivalent will cancel this R equivalent, and then you get equation 3 over there. You'll get equation 3 over there. So now we'll divide inside the brackets numerator, denominator by Rg plus RDS on. Divide numerator and denominator by Rg plus RDS on. So in the numerator, we'll get 1. In the denominator, you'll get 1 plus R equivalent all divided by Rg plus RDS on. And that is what this equation is, equation 4. Now, let's simplify what R equivalent is. R equivalent was the parallel combination of RL and RDS off. Okay, and this combination over here, this combination over here, or this resistance is what we are calling R equivalent. So R equivalent is just RDS off in parallel with RL. Now remember, normally RL is the input to your AC amplifier. RDS off is very large normally. Remember, for a transistor, for most of it is, this is about 10 to the power 12 ohms in parallel with RL. And RL is typically, it will range maybe from 10K depending on the design, or over to maybe 100K. So you see, RL in parallel with 10K is effectively just RL. So that is what we get over here. So from equation 4, I've said, but R equivalent L is just equal to RL in parallel with RDS off, which is just approximately equal to RL. So if you substitute this result in equation 4, instead of R equivalent, we'll write RL. So you'll get that the error, and this is like our onset error or our case 1 error, is just minus Vg, 1 divided by 1 plus RL divided by Rg plus RDS on. So this is our on-state error or our case 1 error. So this is equivalent to our error on, which was our case 1, where series device is on, shunt device is off. So if you look at equation 5 over here, for the error to be small, it must mean that the terms in the denominator must be large. So RG and RDS on must be small. So if you are given a specific transducer, then RG cannot be changed. So all that remains is that the switching device, the RDS on should be small and RL should be large if you want to minimize this on-state error. Now let's consider case 2. Case 2 is when the series device is off and the shunt device is on. So this is the equivalent circuit. So series device, this FET over here is off. The shunt device is on. So this is our equivalent circuit. So ideally in this case, the output voltage should be equal to 0 if the devices were ideal. Because if you had ideal switching devices, RDS off should have been infinity. So the output voltage should be 0. But because these are not ideal devices, we are going to get a small voltage at the output, which we are calling VL. And therefore the error shown by equation 1 over here, and this is equivalent to our error off. So this is our case 2 error, which is the same as our error for the off state of our system. It's given by VL minus 0. 0 is supposed to be the ideal value. So it's just equal to VL. And VL, if you look at this circuit, once again, if we combine the parallel combination of RDS on and RL to be, I'll call it R equivalent. And this is just a series circuit comprising of R equivalent, RDS off, RG. So the output voltage, VL, will just be VG into R equivalent, all divided by RG plus RDS off plus R equivalent. But what is R equivalent? R equivalent is RDS on in parallel with RL. And we know that RL is the input to our AC amplifier, which is typically large, normally 10K to 100K, okay, depending on the design. The RDS on is our switching device when it is on, which is typically 25 ohms, typical 25 ohms. So RL, the combination will be typically just be equal to approximately RDS on. So here I've written that R equivalent is equal to, it's approximately equal to RDS on over here. And therefore our error for this case is just VG. Numerator, instead of R equivalent, we just write RDS on, all divided by RG plus RDS off plus R equivalent. For R equivalent, you can just put it as RDS on. I've not put it over here. I think I forgot to type it over here, but I can just put it as RDS on. I can just leave it that way, equation 4. So if we study equation 4, we can make some observations in this case that this error is minimum if R equivalent, and R equivalent is actually just RDS on, R equivalent is just RDS on, or R equivalent is RL in parallel RDS on. So this error is minimum when R equivalent approaches 0 or is small, okay, i.e. RDS of must be large and RL in parallel with RDS on must be low. So actually here where I've said RDS of must be large, that I'm looking at the numerator, denominator of equation 4. So for this error of equation 4 to be small, the numerator must be small, means RDS on must be small. And in the denominator, if you fixed your source, means RG is already defined, then the only terms remaining is RDS off must be large and RDS on and R equivalent, because this term over here is actually R equivalent. This other term in the denominator is R equivalent, must be small. And this term is our RL in parallel with RDS on. So it must be low. So if we look at the first condition, the condition for the first case for the error to be small, and the condition for the second case for the error is small, we find that in this case, which is what I've written over here, thus in the series shunt configuration, there is no incompatibility in the requirement for minimum error for case 1 and case 2, i.e. for best performance, RDS on must be low, should be low, and RL should be high. So why are RL high? Because I think in case 1, if you look at the equation here for case 1, if RL is high, then 1 plus this term where RL is in the denominator, the higher it is, the smaller the error. But this one contradicts the case of case 2, where R equivalent is actually RL and in parallel with RDS on, because RDS on is typically 25 ohms to 30 ohms. So whether RL is large doesn't matter, because RL in parallel with a small number, a small ohms will still be low. So these are the equations for error of case 1 and error of case 2 for minimum error for the case of series shunt configuration. So I've given some simple problems over here. Compute, because up to now, if you just remain at these equations over here, equation 4 and equation 5 over here, you want to know how does this circuit perform with respect to the series and the shunt chopper until you put some values. So that is the reason for this exercise over here. So compute the errors for the below 3 configurations: series, shunt, and series shunt, given that RG is 1K, RL is 1K, RDS off is 10 to the power 10K, RDS on is 25 ohm. Okay, so this is the case whereby the generator has got a low source impedance. So that's the first part. Okay, then case 2, you're told to repeat for RG is 100K. So this is a high resistance source, but the load resistance RL is still the same, and the transistors are still the same, because RDS of is 10 to the power 10. Then part 3, repeat again. For RG is 100K, means this is a high source impedance. But now RL is also high, and the devices are the same. So in effect, over here, this is just very simple. So you'll make a table, which is what I showed you last time. So you can start with the shunt, then series, and then let me hit the space. Then series shunt. So you can get results. Actually, let me just start again. Let me put it here. So for each of these, this could be said like your shunt switch. So these are the errors. So the on error of shunt, off error of shunt. Then you go to your series. Then you go to your series shunt. And you can start with, so like the first column will be like for RL is 1K and RG is 1K. Then the second column here will be for RL is 1K. RL is 1K and RG is 100K. No space for me to write. Okay, and then the third one, the third column will be for RL is 100K and RG is 100K. There's no space for me to write it over there. Okay, and then for this first column over here, by looking at the results that you get, by substituting the equations that we've derived, you'll be able to tell that if RL is 1K, RG is 1K, then the best switching configuration to be used should be this. And you'll find in most cases, it will be series shunt. It will be series shunt. It will be series shunt. Now, I want to do it, you can just do it. We'll derive the equations, you just substitute the values over there. Now, the other type of error for this configuration is referred to as the errors due to switching spikes, which are not included in my notes over here. I'll just start with the practical circuit. The errors due to switching spikes. So remember, these signals are being driven in antiphase. So this is our series switch. This is our series switch. This is our shunt switch. This is your RL. So for errors due to switching spike, we can assume that your VG is equal to 0. So we're just investigating the effects of the interelectrode capacitances, the effects of our interelectrode capacitances. So you know that the capacitances in the devices so if our generator is 0, so if we just to observe the effect, let's assume this is our first gate and this is your second gate. You can draw some timing diagram over here. You can make them big. So this is the gate 1 voltage. This is your gate 2 voltage. So if you consider the output due to the driving gate voltage due to gate 1 only, I'll call it V0 as a function of gate 1. So you're going to be getting, I'll start from here, this interval, you're going to be getting spikes like this. And V0 due to gate 2 only. So for this one, you're going to get a spike, something like that. And therefore, V0 as a function of gate 1 and gate 2 will be approximately equal to 0, because the polarities of the switching spikes will tend to cancel one another. So in other words, the series shunt configuration offers the best switching spike performance, because the spikes caused at the output, or the switching spikes caused at the output as a result of the interelectrode capacitances tend to be almost same in magnitude, but opposite in polarity. In other words, the series shunt configuration gives us the best spike performance of all the other switching configurations. And the simple exercise that I've given you to put some values for the on and off error, you'll find that the series shunt also gives the best error performance. So with that, we come to the end of this session. Let's continue. I've just missed it in my notes over here, but it's actually quite simple. We did it for the spike performance for the series and also for the shunt. So you can combine the two and to get the spike performance for the series shunt. Now in the lab, if you use a transistor or an FET, which is designed for chopper, those switching spikes are actually very, very tiny, very, very tiny. they're almost negligible because these capacitance are very small. Let's see. These capacitances are very, very small. So this is a transistor I've always been looking for. It's called the 2N4856A, and it's designed for chopper amplifiers. As you can see where it's designed for both analog switches, sample and hold circuits, and also chopper amplifiers. And they give you RDS on 25 ohms. They didn't give us the RDS off over here, but I just wanted to show you the capacitances. Here's some capacitances. So look over here. The common source means this is the capacitance between the gate and the source. It's typically on average about 10 picofarads. And then this one has only given the capacitance between gate and source. They did not give us the capacitance between okay, this is capacitance, gate and source. So this is what I was telling you. If you look at this curve, this graph to the right over here, the x-axis is the gate to source voltage. So let's assume that we are switching between maybe 0 and -4. For VDS is equal to 0, you can see the capacitance will range from almost, each of these divisions is 3, I think, in the y-axis. So when it's 0, the capacitance will be 6 plus 3, about 9 picofarads. When you switch it to, when you put a voltage of -4 volts, maybe to switch it off, the capacitances change to 5. So the capacitance is dynamic, it's not static. And that's when the analysis that we did, we assumed that the capacitances are stationary. But here, all I just wanted to show you is that these capacitance values are very small. In this one, they didn't give us the capacitance between the, in this one, they're not giving us the capacitance between either intellectual capacitances. Let's see this one of on semi. So even this one, the capacitance is 10 picofarads. They've not given us another capacitance. Okay. You know, these capacitance typically are small, and they're quite small. So let's go back to our notes. So please do this simple exercise. Please do this simple exercise. We derive the equations, just a matter of substitution. Okay, now I think here are some of the practical circuits that you'll be doing in the lab. Some of the practical circuits that you'll be doing in the lab. Here we're using the 2N4856A. This is an American transistor. So these two transistors are the same. So these are series shunt chopper. So these two transistors are the same. There's actually an error in the values of this bottom resistor here. This bottom resistor is actually 22K. This bottom resistor here is 22K, not 2.2K. So this Q1 and Q2 forms our antiphase circuit. Q1 and Q2. This forms our antiphase circuit. All it does is provide two voltages which are 180 degrees out of phase, 180 or 90 degrees out of phase, so that when one signal is going up and the other signal is going down. So how does this circuit work? I'll just explain it very simply. So the function of Q1 and Q2, this BJT transistor, is just to give two signals at the gates of VG1, the top transistor, so that when the gate of the top transistor is going high, the gate of the second transistor, VG2, is going low. I.e., when the top transistor is on, the bottom transistor is off, and vice versa. So let's see how this circuit works. So actually, at the extreme left, you are going to be providing a control voltage here, which will be typically less than 5 volts with the reference minus 10 volts. So this is your VC or T. This is your control voltage. So the 1.2K is for protection of the base emitter junction of the transistor. So let's assume that you've designed it correctly. The only thing in the design, you got to make sure that this transistor Q1 is driven to saturation. So the maximum saturation current of Q1 is what? The maximum saturation current when this transistor Q1 is completely on, I'll put it here, IC of Q1 max will just be equal to 20 volts divided by 2.2, 2.2K. Milliamps. So it's approximately 10 milliamps, so slightly less than 10 milliamps. And the base current of Q1 times the HFE of Q1 should be equal or greater than IC max. So if you're to design this in the lab, let's call this one IB. The proper IB for the design, because it should be able to drive Q1 into saturation. So IB will be equal to the peak value of the C of T minus 0.7 volts. I think that's getting messy here. Let's forget it here. So IB should equal to VCT minus 0.7 over 1.2K into, I'll call it beta 1, where beta 1 is beta of that. So if you're doing the design, you got to ensure that that's how we get IB. Hey, what am I doing? Let's remove this beta first. Okay, that's how we get IB from that equation. And therefore now we can get IC. So to get IC, IB into beta 1 should equal to IC Q1. This should be Q1 max. Okay, so if you're designing the components, this is the equation that must apply. You must ensure that when the base current flows, base current times beta should be greater than the current required to saturate that circuit. So that because we are not designing an amplifier here, we're designing a switching circuit. So when the circuit operates between saturation and off. Okay, so let's assume the design is correct. The resistor 1.2K just used for protection of the base emitter junction of Q1. So let's assume our design is okay. So Q1 will be driven on and off, on and off, on and off, on and off. So when Q1 is on, what happens? When Q1 is on, the voltage between the emitter of Q1 and the collector of Q1 will be approximately 0.2 volts for silicon transistor. Let's just use silicon transistor, not germanium, because it's the most common in the lab. So it will be 0.2 volts. So it means that Q2 will be off, because to bias Q2 on, you need at least approximately 0.7 volts. So when Q1 is on, Q2 is off. And when Q2 is off, what is the voltage at the collector of Q2? Let's call this point the collector, let's call it A, and the emitter of Q2, let's call it B. So let's just draw an approximate graph over here. So let's call this first part to denote VA, VB. And I've also forgotten my other curve, which will represent the driving voltage. Okay, so let's assume that the transistor is on Q2. So these are all of Q2. If Q2 is on, what is the voltage at A? What's the voltage at B? So when Q2 is on, the emitter and the collector is like a short circuit. We can neglect the small voltage of about 0.2 volts. So the voltage at A, and we'll consider them with respect to the ground. So the voltage at A with respect to the ground will be what? Okay. So I think we have to start. A better way would be to start with the transistor initially off. So let's start with the Q2 off. So when Q2 is off, point A and point B are like they're isolated. So the voltage at A will be 10 volts. And the voltage at B so this is a 0 volt reference. Remember, Q2 is acting as a switch. So when Q2 is off, it's like point A and point B are separated from one another. So for example, if I was to draw the switch here, this point A, this is point B. So when it's off initially, the 330 ohms goes to the 330 ohms connected to point A will go to positive 10 volts, and the 330 ohms connected to point B will go to minus 10. So the voltage at B would be something like this. So this point would be minus 10. And simultaneously, this capacitor, the 50 microfarads capacitor, will originally charge to plus 10 volts, minus 10 volts across it. Because if AB is short-circuited, is open-circuited, if you look at this diagram I've drawn of A and B here, you have a capacitor going to the ground via diode. So current will come down this way and the capacitor will charge this side positive, this side negative. So next, let the driving voltage cause the transistor Q2 to come on. So when it comes on, the voltage at A will become 0. The voltage at B will become 0. So we'll have a situation like that. I've not drawn it, but maybe let me change the colors. So maybe it becomes this point over here. So it will be 0 volts. So this corresponds to transistor is on. Transistor is on. But now let's observe what is happening at the gate of our top transistor. The top transistor, which I've written VG, the gate is VG1. This one, the gate is VG1 here. So it must mean that initially when transistor Q2 was off, the capacitor, the 50 microfarad capacitor had charged with the left side positive, almost 10 volts. The negative side of the capacitor is grounded through the diode 1554. So initially it had charged through this circuit here to the ground. So this potential here is approximately 0 volts. So when the device was off, that was the situation. So it must mean that the voltage VG1 is equal to 0 volts times 22K over 100K plus 22K, which is approximately equal to 0. And therefore the top transistor was on. The top transistor was on because now I'm running out of space over here. But, but I hope you're following. I'll do it in a clear circuit. Now, so when Q2 was off, it must mean that the top switching transistor, the 2N856A, was on. And let's look at point B when the transistor was off. When the transistor was off, let's look at the circuit at point B when Q2 was off. When Q2 was off, the voltage at the gate of VG2, this voltage at the gate over here, remember if it's off, it's like point A of Q2 isolated from point B. So it's point B is connected to the minus 10 volts through the 330 ohms. So when the transistor was off, when transistor Q2 was off, then the voltage VG2, which is driving the shunt transistor FET, must equal to minus 10 volts times 22K over 100 plus 22K. Now that voltage is designed to switch off. Let me just see. That's 22 divided by 122 times 10 volts. So this is working to about minus 1.8 volts. So this voltage we'll assume it's enough to switch off FET2. Let's assume the top one is FET1. I hope you people are following. So next, that is when Q2 was off. Now when Q2 turns on, then point A and B of Q2 are like short-circuited to one another. So in this circuit, it's like this one connected between point A and B. And the capacitor, which was charged to positive 10 on its positive side, is now like it's connected to a zero potential because the 330 ohms at the collector of Q2 and the 330 ohms connected to minus 10 will form a circuit like this. Let me draw it over here. So this side is minus 10. This side is plus 10. We got 330. We got 330. So this is the point where the capacitor is connected to. And originally this side was plus 10. So plus 10 is connected. So it's like a minus voltage. A minus voltage because now the diode will be reverse biased, so the diode will not come into play. So you'll get a minus voltage, a minus 10K to the gate of FET1. And this 100, this 22. So we are going to get again minus 1.8 volts connected to the gate of the top FET. And at that same instant, when the switch closes, that's an instance when the switch closes, what happens to point B? What happens to point B? At that same instant. Let me draw it in a clear paper. So these are just coming through potential dividers. This is your top FET. So these are the ones which are going through point A and B, but the top one is going through a capacitor. So that transistor, I'll just represent it to the switch. So So in this case, the second case was when this switch is closed. So when the switch closes, we've analyzed what is going to happen. So when the switch closes, this one becomes off because this capacitor had charged to this side, positive, negative. So it's like putting 10 volts, because remember now here is 0 volts. Because we've got a potential divider formed by the 330 ohms connected to 10 volts, another 330 ohms connected to minus 10 volts, connected to minus 10 volts. So point A and point B is approximately 0 volts. So we've already shown that the top transistor will be off. Now, what about the bottom transistor? The bottom transistor, the voltage at the gate, I'm calling it VG2. So VG2 will be equal to how many volts? To be equal to minus 10. Actually, the potential, this negative is here. It's connected to this at this point over here. So the potential from here to here is actually 10 volts with this side positive, this side negative. So VG2 with respect to the minus VCC, if you consider this is minus VCC, which is minus 10 volts, the potential between the source and the gate of VG2 is actually a positive potential. So it will be 10 times 22K all divided by 100 plus 22K, which is positive 1.8 volts. So it means this one will be on. This FET will be on. Now the process will repeat. And the process will repeat. So next is what is going to happen is that point A and B will open. So when point A and B is going to open, then the top transistor will give about 1.8 volts to drive FET1, and the bottom transistor will be connected to the minus 10 volts. So the bottom transistor, VG2 will be minus 1.8 volts to FET2. So that's what is going to be happening. So I hope everybody has understood. So if you were to draw, say, a timing diagram of, say, a VG1 and VG2. So when this one is on, this one is off, and when this one is off, this one is on. Okay, so this is 1.8 volts, and this point here is minus 1.8 volts. So the same will apply. Minus 1.8, 1.8 volts. So for this design, you've got to select your transistors very carefully, that in order to switch them off, you need at least minus 1.8 volts to switch it off. So I hope that is understood. Let's just go to the transistor. Let's see. Like if I to use this transistor over here, this one requires a VGS of minus 10 volts. I'd like to switch it off. But there's another one we saw which is quite sensitive. So anyway, that is for the design. Let's try the other transistor on semi. I remember there's a transistor we found. Oh, that was a Texas instrument. Like this on semi, to switch it off, to switch the drain off for various values of VDC. The smallest voltage I'm getting over here is minus 8 volts. So you got to select your transistors very, very well. Texas Instruments, let's see. Oh, well, let's try this one, funnel. In this funnel, you need at least 5 volts to switch it off. The smallest voltage to switch is 5 volts. Okay, let's get out of here. So actually in the design, you need to change maybe you'll need to change this bottom resistor over here, this 22K, to be slightly higher if you need about 5 volts. So maybe if the peak is 10, so 10, you can design it. You can just say that because the peak voltage swing is 10 volts times their non-resistance, let's call it Rx, over 100K plus Rx should equal to, say, 5 volts peak to peak. Then you can solve for Rx. So that's how you design for the second resistor. So for the data, remember there was a Texas Instrument FET, which was very sensitive. You could switch it off with about maybe 2 volts. And like the ones which I've just shown you here, the smallest value we are getting is like 5 volts to be able to switch the device completely off. Okay, so this is the series shunt chopper, a bit of its working. If you're using two same devices for the series switch and shunt switch, you need an anti-phase circuit here to be able to ensure that when one FET is on, the other FET is off. Now there's a simpler application over here. Over here, the anti-phase circuit is just the same. You can try it out. This resistor is actually 22K, not 2.2K. Just from the same example. So this This op-amp is just simulating the an AC amp, because the gain of this circuit is approximately RF 10 meg divided by 100. Approximately, I said. And this is an offsetting circuit because all op-amps will have an output offset voltage, which should give rise to problems, like drift problems. So they use an offsetting circuit to ensure that when there's no signal, the output is zero. And I told you also that in the lab, to use these choppers, all you need to do is to connect an oscilloscope to the output of the chopper and then raise the value of the chopping voltage or the control voltage so that the device is just able to switch on and off. Otherwise, if you use a large control voltage, then switching spikes might appear at the output, which we don't want. So there's a simple example over here which you can do. And then there's another application over here where we use an N channel and a P channel. So if you don't have an antiphase circuit, you can use an N channel and a P channel FET or a CMOS combination. So when one device is on, the other device is off, and you feed them with the same voltage, just like your CMOS logic gates. So we can conclude and say that I've said here that the above theory has been based on FETs, switching devices, but due to enhancement in technology, these choppers are now implemented using CMOS and the MOSFETs. CMOS are just MOSFETs actually, but they're fabricated in one chip. When you talk of MOSFETs, they're discrete devices, but you can build an equivalent CMOS circuit just using MOSFETs. Just like in digital electronics, you studied TTL, but inside TTL, they are just BJT transistors. So nowadays, we normally use CMOS implementation or using MOSFET implementation because of the following reasons. Number one is low cost of fabrication, low power consumption, high switching speed, low power drive. So the CMOS or MOSFET based implementation have got these following advantages. Now, in conclusion to this topic over here, I've said that from the results of the performance of the three configurations. Now, these results are obtained by putting values. That exercise I gave you earlier, to put real values for RL, put real values for RG, then find out the error caused by the shunt, error caused by the series, error caused by the series shunt. Then from that table, you'll be able to select which configuration gives the best error performance. And as I've told you earlier, if you do that exercise, you'll find that the series shunt outperforms all of them. And also the series shunt has got the least spike errors or errors due to switching spikes, because the spikes at the output due to the series device tends to cancel out the spike due to the shunt device. So those conclusions, I've written them over here. So number one is that when the load resistance is low and the switching speed is not important, the most convenient configuration is to use the series chopper because of its low net error and its small component cost. Because they are using only one transistor. although nowadays the cost of transistors have become so cheap. Now, number two conclusion is that when the load resistance is high and the switching speeds and feed-through spikes are important for the low-level signals, then the series shunt chopper offers the best performance. Remember, the higher the switching speed, the lower the reactance of the interelectrode capacitance, the greater the possibility of feed-through from the control signal to the output to the load. And I've just shown you that for the series shunt, these switching spikes tend to cancel one another. So this series shunt chopper offers the best performance. And finally, number three, conclusion is that the shunt chopper produces relatively large errors. That's from the table. There's a table I've given you in the notes, which I worked out the values. It's there in your notes. So the shunt chopper produces relatively large errors, although its spec performance tends to be better than that of the series. It has a higher switching capability than that of the series chopper, but its error is just too large, so we don't use it. The only other observation is that we said that the series shunt chopper is not very good if the capacitances you're going to be using to the load is very large. But in the case of the chopper amplifiers, the capacitances we use are normally in terms of nanofarads. So this is not a disadvantage for the case of series chopper. Now, maybe you can switch on your phone, those who've gone to the labs and done this experiment. Can somebody tell me some results you've been obtaining? Have you done this experiment? Just switch on your mic. Anybody? Nobody is switching on the mic? Okay, Sierra, Okedo, Safin, switch on your mic.
I've not done the experiment.
You don't done the experiment? Has your friend done what are the experiments you're doing in electronics, 50 year?
I've not yet gone to electronics lab.
Yeah, log amplifiers, anti-log, and multiplexers.
Okay, Marigo, have you done just repeat again? Repeat again.
Actually, I'm going there on Tuesday. I've not been there, but at least I know from the manual we are doing.
I can't hear you. Yeah. Are you using a phone? Are you using a phone for speaking? Hello?
Anti-log amplifiers.
I can't hear you clearly. I don't know whether your mouth is very close to the microphone or
Can you
what,
hear me?
or the speed is so slow. Yes, yes. Continue.
I'm saying,
yes,
from the lab manual, I understand electronics lab. We are doing log amplifiers, anti-log amplifiers. We are doing choppers and multipliers.
Yeah, that's what I'm asking you. Have you done the chopper? Have you done the chopper?
I'm doing. Our group is going there on Tuesday, so we haven't started yet.
And you don't know any friend who's done the chopper?
Yeah, 2 groups which have already done, and I'm sure they are maybe they can respond.
And they're refusing to. Okay, thank you. So let's continue. So this is the conclusion to this topic. So please, you got to do some problems. The problems are quite simple, but they're quite lengthy. So these are some of the questions I asked in the exam, and only about 50% of the students get it right. Question 1, define a chopper stabilized amplifier, stating its method of operation. Hence state the applications to which it is well suited, giving examples. The principle of operation. Most students do not know the principle of
Excuse me,
operation.
sir.
Yes.
Before you continue, I wanted to ask if okay, you said that the feed through spikes are actually obtained from interelectrode capacitances. I
Yes.
wanted to inquire if the capacitances that we have in the circuit also contribute to feed through spikes, or it's only the interelectrode capacitances.
Which capacitance do you have in the circuit? See, like, I'll show you here. Like in this diagram over here, the capacitance are just to aid the switching off and on of the FET because of the gate charge. The gate charge. Okay, but let's get a simpler circuit. Wow, this one I've already done. I'll put a lot of things on it. And let's use this bottom circuit here. It's the same thing, only that this one's got an amplifier on top. So for example, in this circuit over here, the switching device is only this top, the 2N4856A, and the bottom one, it's not very clear, it's also the same transistor. So this capacitor, 50 microfarads, is only used, this capacitor is only used to perform the anti-phasing, which I explained. This capacitor here is only used to perform the anti-phasing. Okay? So the switching spikes, if this VG is 0, if you ground this input to ground, and this signal comes to switch the devices on and off, then we'll get switching spikes at the output over here when this device switches on. And we did it. We have spent a lot of time trying to analyze this circuit using linear analysis. Why you are not there in the class? Why you did all the equations? In fact, I'm going to ask it in the CAT. The control signal can pass through the gate to collector through the capacitance, which you call CGS. It can also pass through the gate to drain capacitance, and then from the gate to drain also pass through the drain to source capacitances. Okay, so switching spikes are just due to inter-electrode capacitances. Okay, I did a simple analysis. In fact, I should give you assignment because this is actually like third year work. I should give you another assignment to to draw. So this is our series shunt switch. These two transistors here is the series shunt switch. Okay, these values are these bottom values are wrong. They should be 22K or a bit more. All right, so or the other way is you can double this the supply voltage to be maybe plus 20 minus 20, then this will be okay. So you can draw an equivalent circuit and analyze it from here to here, signal flowing from the gate to the top over here through the. Okay, let me just draw it. I don't know, you people, you were there with me in class. So in this circuit, you can have an equivalent circuit like that, like that. Or this is C DS, this is C GS, and this is C to G, and those are all reactances due to the capacitance, and same over here. Okay, and then you analyze this circuit. This circuit actually is wrong. There's not supposed to be a resistance here. Okay, so you can analyze that. But in the lab, I told you that because these capacitors are small, I've showed you some, most of this, the largest capacitance we are seeing is around 10 picofarads. And the reactance of 10 picofarads to the fundamental XC is approximately 1/2 pi FC for the fundamental frequency. So if C is 10 picofarads, this is 10 times 10 to the minus 12 farads. So you'll find the reactance is quite small. Okay. And this is the switching frequency. This is the switching frequency. And since the voltage that we want to switch is a very slow varying voltage, I told you the frequency, the period of the frequency could be maybe half a day. It could be. Okay, so you don't have to switch at a very high frequency. Okay, because from Shannon's theorem, for us to extract, to recover all the information inside a signal that is sampled, you only have to sample it theoretically at twice the frequency. Okay, so if the period of the signal is, say, even half a day, or even if the period of the signal is 1 hour, and your control signal square wave frequency or rectangular wave frequency is maybe even 100 hertz, it's more than sufficient. Is that okay? No, you guys are taking me behind. The gentleman, was it Odwar who called me? Odwar?
Yeah, I think it's clarified now. I think it's clarified.
And today I wanted to do more. Okay, so finally, most of the questions in the exam will be to find the overall error of a chopper stabilized amplifier system. So a chopper stabilized amplifier system has got 3 parts. Okay, like this example over here is to show you this is the modulator, and we've got an identical circuit over here, which is the demodulator, and this circuit in the middle over here, comprising of the op-amp, is your AC amplifier. So for example, in this case, the capacitor to your AC amplifier is 1 nanofarads. The input resistance is 100K. The feedback resistance is 1 mega ohm. So it means that the gain of our AC amplifier is approximately 10. Okay. So this circuit can be divided into 3 parts: the modulator, which is a series shunt switch, the AC amplifier with an input capacitor 1 NF and an output capacitor 1 picofarad, and then the demodulator, which is identical to your modulator. So the problem will be, how do we get the total error? So to get the total error, you go to get the maximum error. That's why I told you to do the exercise, put values, and we've calculated some the theoretical values. So you can just substitute the values for RG, values for RL, values for RDS on, RDS off. Okay, so you get the on error, get the off error. So use the maximum, which is greater. Is it the on error or the off error? Use the maximum error you get. So if you're given a circuit like this with the 3 stages, then the error, I've just drawn here, the error, so this block diagram, this is your generator signal VG that you want to amplify your slow varying VG. So you got your modulator, you got your AC amplifier with capacitors, you got your demodulator here. So if the modulator generates an error which is equal to error 1%, your AC amplifier generates an error, which you call it, say, error 3%, and your demodulator generates an error, just say error 2%, then the error total at the output will just be the sum of the three errors. Error 1, error 2, error 3. Okay? That's how we get the total error of the signal when it's transmitted from the input to the output. Okay? And you can compare it with the error which would have been generated if there's no AC amplifier. So for example, if, for example, there's no AC amplifier, supposing in this circuit over here, supposing the capacitor was not there, we just had a direct short. So this just becomes a normal inverting amplifier. At the output over here, this capacitor 1NF was not there, just had a short over here. Then this circuit is going to generate a lot of errors due to VIO, or VIO drift, right? Because any VIO at the input would be magnified by the gain of the system to appear at the output. In the AC amplifier, you can also analyze this circuit this way. Supposing this modulator is not there, supposing the demodulator is not there, and capacitance at the input is not there, capacitance at the output is not there, means you just have your normal op-amp circuit. Means there's no signal coming from the modulator. Then the output at point Y of this will be just be the signal due to VIO of the op-amp. It will be the signal due to VIO of the op-amp. All right? And it will actually be amplified by the gain of approximately, in this case, 10. But since we've got, if you put the capacitance, you forget about the modulator. Now you just ground point A to the ground, compute the error, the signal coming out of the output, which will be a signal due to VIO. Then the gain of the amplifier will be drastically decreased because the signal referred to the input circuit now, which we call RI, will be an impedance, which will be, you combine all this 1NF, 100K, be one impedance, say Z1. The feedback resistance, you can call it Z2. So the output at point Y will be given by minus Z2 over Z1, where Z1 is root of R squared, which is 100K squared, plus root of reactance of 1NF squared. So you'll find the signal at point Y, which will be much, much less, and then it's going to pass through this 1NF. So this is actually acting as a filter. It's actually acting as a filter and thereby decreasing the drift signal of the op-amp that appears at the output. And I wanted to do more than this, and my time is over because of the problems I had with my computer. So any more questions on this? So please do these simple problems over here. I normally ask this. What are those questions? Oh, here. Question 2. Distinguish between series shunt, series shunt and series shunt chopper. Hence state the criterion used to select a particular configuration for a particular operation. That's from the table and also from the summary. It said if you want something cheap, a low cost, use series chopper. If you want a high performance circuit, use series shunt chopper. Then here you're given figure 3. So figure 3 is a chopper stabilized amplifier. Input is 20 millivolts DC. The maximum drift voltage VAO is 0.001 cos 2 pi t. So cos 2 pi t is equal to 1 hertz. Okay. So this should have been written as omega t. Omega is 2 pi f. So 2 pi f means instead of f over here in this bracket, f is 1 or 1 hertz. So for the circuit, determine the drift voltage magnitude at point Y. If the input to the AC is shorted, so they're asking, where is it? It should be here. So they're asking this one. This is your point Y. So point A is grounded. What is the drift voltage? So that's just very easy. So just the gain of this amplifier, use Ri to be root of 100k squared plus root of reactance of 1 NF. You get the signal at point Y. So that is it. So the hint is just cos omega t, omega is 2 pi f, f is 1 in this. So it's 1 hertz signal. Next, you're told to determine the maximum error at the output of the chopper stabilized amplifier system, given ideas on that. Chopping frequency is that. So I've shown you, you get error of modulator, error of AC amplifier due to VIO, and error of the output stage. Then you're told state what can be done to improve the performance of the circuit. So this is actually the circuit over here. So what can be done to improve the performance of this circuit? What can be done to improve the performance of the circuit? We know how to improve the performance of the circuit. Number one, use the lowest frequency that is possible. Use a sinusoidal drive. Okay. Then optimize the modulator and demodulator to give you the minimum switching spikes. That is it. Do you have a class after this? CR? CR?
Yes, we do.
You have a class. Okay, so please do these simple problems. And the next class, we are going to start log amplifiers. We are going to start log amplifiers in the next class. So if there are no questions, I'll stop over there. I'm very sorry I started late because my computer was giving me problems.